So welcome everyone to the first invited lecture of the IGLU competition. I am very happy to welcome Marc-Alexandre Côté from Microsoft Research. He will give a lecture titled ALFWorld, Aligning Text and Embodied Environments for Interactive Learning. Before we start, I would like to give a short biography of Marc. So Marc is a senior researcher at Microsoft Research Montreal since 2017. Before that, he did his PhD at the University of Sherbrooke in 2017. His research interests are, generally speaking, deep generative models, neuroimaging applications, reinforcement learning, and language understanding. And he was the leader of the TextWorld project that aimed at developing new RL agents that are capable of navigating and interacting with text environments. So I would like to thank again Marc for this invited lecture. And Marc, the floor is yours.
Thank you, Mohammed, for this good introduction. It's my pleasure to be here, and I can present some of my work, recent work called ALFWorld. So I was planning on actually making a small bio because I wasn't sure if I get introduced. So I guess I will go really quickly on it. So as Mohammed mentioned, I researcher at MSR Montreal. So Montreal is in Quebec, part of Canada. So for if you want to see where it is exactly. So this is really big, but only the bottom part of Quebec is actually has some decent population. So really close to Montreal. So it's all the way down. And like Mohammed mentioned, so I went to University of Sherbrooke, which is also in Quebec. I joined briefly Maluba before it got acquired by Microsoft, and since then I'm working at Microsoft. So back to the talk. So in this lecture, I want to give an overview of one of the recent projects that I've been working on with a former intern called whose name Moed Shrida from University of Washington. And so everything that I mentioned here is in the paper, and we also have a website, and code is also available online. And this work was done in collaboration with other people from MSR and CMU. Another title for this talk, or I guess research interest that I have, is really like, how can we leverage language or abstract planning for better interaction? So it will become like clearer in during the presentation that what I meant by abstract planning is more like in terms of reasoning using a language. And just to give you like a real life situation, let's say you are invited to a friend's house and you're asking them, oh, I can help you with the dinner, and your task is to slice some apple. So even before you go in the kitchen, you step in the kitchen, you can already have some kind of plan in your head, even though you haven't looked at the actual kitchen. But then when you have, so maybe this plan involved like just, okay, I'll need to a knife and some apple and maybe something to cut the apple on in a plate. So you already have those in your mind. And then when you arrive in the kitchen, it might look a bit different from what you expect, and you have to adapt and iterate like that. And that's what I mean by abstraction. So you can create like a mental image of the environment. So what I refer to concept. So you know, this kitchen usually have cupboards and drawers, which might contain knife, or maybe it's in the sink because it was dirty or something like that. And you can draft the plan based on those concepts. And the language is a really powerful tool to manipulate those concepts and really quickly adapt your plan. Along those lines, so another research interest of mine, and that is, I guess, addressed in this paper, is how do you teach machine to interact with the human world? So regarding interaction, like teaching an agent to interact, usually one of the most used paradigm nowadays is reinforcement learning. So that is used to teach agent how to act in a particular environment. And because it's a guest lecture and as a mentor, so I'm not sure if everyone is aware of reinforcement learning in the group. So I would just briefly mention, this is like a really typical diagram of a reinforcement learning process. So you have an agent that his task is to perform action that is sent to an environment, and the environment will change depending on the action, either giving some reward or updating the state. And then the agent has to iterate over based on those new observations. So a concrete example could be like the environment is a game like Minecraft, and you have a Steve, which is a player, and he perform an action like jumping. And then the state is changing from, okay, now I'm jumping over a fence, and maybe there's some reward depending on what you're trying to accomplish. And then and the other tool that is used for, I guess, this teaching human to interact with the human world is language, because the language enables certain interaction, like interacting with humans. So through conversation, you can think of personal assistant, and also with the human knowledge. So reading book or documents or Wikipedia or the whole internet. That's where we encode most of the human knowledge. And so one of the so those two tools, or those two things that we are interested in, when you combine them, one of the test bed is text-based games. So text-based games, if you're not familiar with them, is something that it's a type of game where you only get observation as text. So you're getting text of where you are, like your surroundings. So here you are in the middle of the room, you see a dining table, a stove, microwave, cabinet, and you get some goal some of the time, and then you're given a prompt, and as a player you have to type what do you want to do in this environment. So you have to type the actual command, so maybe go to the cabinet, and then you get some feedback in response to this interaction, and then you continue like that, so back and forth, and until you manage to achieve the goal, so which was putting the pan on the dining table. And so while text-based game exists and they were created for human pleasure, like playing those games, they are really challenging in terms of if you want an AI agent to solve them. And so that's what pushed us to build TextWorld, which is a framework that is able to generate an unlimited number of interactive environments. And we can vary the complexity by the length of the task, or the density of the reward, or the whether it's your action are deterministic or not, and the number of action, and so on. So we have like full control on that. And what we can also do is not just train your agent on one single environment and test it on the same environment. So we can have like a proper trained test valid set, which is at the time was not common for RL training. Which leads us to ALFWorld. So ALFWorld is actually a framework that combines two other frameworks. So there's one which is like a 3D embodied world. So we have a realistic graphic here, at least realistic looking graphic of the environment. So it's like super simple. It's in a house, and you have some object you can interact with. And what we did for this particular work is we combine it with TextWorld. So we had an alignment between the embodied world and a text representation of that world. So we can actually track what is happening, one in the abstract space and the other one in a concrete or the simulator. And what we wanted to focus on is planning on the coming up with a plan in the abstract space before carrying it in the embodied world. And by doing this, we hope the agent could learn some typical affordances of what you can do with a particular object, or common sense. Like if you're looking for an apple, you're going to look in the fridge, not in the trash can, if the goal is to eat it. And we want to study transfer learning. So again, we want to make sure that we are training and testing on a different set of environment and task. And ALFWorld is based on the ALFRED dataset, which is a collection of seven different tasks with a lot of different environments. So there's different rooms in the house with different objects. And as part of that dataset, we also have access to some goal annotated description. There's like 25K annotation for this particular framework. So in the ALFWorld experiment that we run, we didn't focus on the instruction. So the instruction is more like into in-depth description of what the agent has to accomplish. And we're more interested in, okay, given this high-level goal, how do you derive this plan in this abstract space, which is in the text-based game, and then carry it out in the simulator. So just a technical overview. So we in order to get this alignment between the two environments, we rely on PDDL, which is a description, a language for describing planning problem, and we have kind of a well alignment, so we can use those PDDL domain and problem to generate a text-based game from that. And this is also used in the ALFWorld, the ALFRED dataset that was used to get the Oracle trajectory as well. And now I'm going to move on the first attempt at solving or creating an agent that is able to exploit the TextWorld engine and interact in this physical environment, or the simulator. We call it a bottler, so building understanding in TextWorld via language for embodied reasoning. And so typically, when you are trying to solve this type of environment, like a visual 3D environment, you're going to have some state estimator. So this is what is actually looking at the scene, trying to extract some objects from that. And then the controller is responsible for producing like a low-level action. So move a couple of meters in front of you, turn the camera, grab an object, or turn on something. And then you iterate over like that until you manage to accomplish the goal and get some positive reward. But we want to leverage TextWorld engine. So we added a new module, which we call the text agent. It is similar to the brain that is trained using the TextWorld engine. So this is kind of a pre-training step where this text agent will experience a similar type of environment that ALFRED provide. So we are going to provide a text description of what the agent is actually looking and what is the goal. Then the text agent would have to come up with some high-level command that will solve this particular goal. And once it is trained, what we want to do is take those high-level commands and send them back to the controller. So they will act as a sub-goal for the controller. So the controller would have to still operate in the low-level action regime, but it can condition on both the state estimator and the sub-goal, that is the high-level command that is outputted by the text agent. And as input to the text agent, how we get this text observation is by converting our state estimator to some sort of captioning. And we'll go into more detail just in a couple of slides. But essentially, we're going to try to run like an object detector on the image and try to classify what are those objects. And that will compose our text observation that is given to the text agent. Like I mentioned, we are going to focus on the vision part. So in this work, we try to use a mask RCNN. So it's just like it was pre-trained on a different collection of objects from the environment and a lot of images. And then we have kind of a heuristic or template grammar that will convert what has been detected to just a series of observations. So you arrive at certain location. So the room is divided in different zone areas. and we call them location 1, 2, 3, 4, 5. So they don't have like a particular name, but they correspond usually to you're in front of the countertop or in front of the sink or something like that. And you can see that on the countertop 1, you can see an apple and a potato. And we use those IDs at the end because in this particular environment, you can have multiple objects of the same type. And we want to get a way of to differentiate between those like two entities of the same type. Eventually, what we want to go for is more replace this naive detector with like a full captioning. So that will be closer to what human might want to would describe an image to, let's say, your personal assistant, if you want to say what you're looking at the moment. But this is future work. Then we're going to move to the controller, just the body part. And this is, we try a couple of different things here. We didn't want to, like for this particular word work for ALFWorld, we didn't spend too much time trying to learn that part. So that will be on a subsequent work that we're working on at the moment. But so what we did try to do different approach for the controller. So we have this A star, because we have access to the PDDL file, we can actually run a graph search algorithm that will move the agent between those different locations that I mentioned. This helps us to just reduce a bit the complexity of having to solve navigation as part of this already challenging task of finding a mug and putting it in a microwave, let's say. We also have like another navigator which just teleport instead of just running in the environment. It just run a bit faster. And also there's some failure point with the A star navigator, where if the agent is trying to move toward an object, between the dining table and a cupboard, and if the cupboard doors are open, it actually blocks you. But the A star navigator that we had at the moment didn't compensate for that. So that's one way that the Oracle navigator with the teleportation is actually yielding a bit better result. And like I mentioned, what we would like to do is train a vision language navigation agent. So the controller will be trained either end-to-end or some other form of training. In the last part, the last module, the Butler brain. So this is the text agent. So this is really a high level overview of what is the structure, the architecture that we use. So we have the input. So we have the goal that is provided in text. We also have those observation history. So the past, and this is an hyperparameter, couple of last observation. So you were in front of the countertop, or you are in front of the dining table, and on it you see some objects. And we also have the original observation, and this is just a kind of a typical for this particular environment, where the first observation is more telling you about what are the different locations that you see in the area. It's kind of you're just scanning the room once you enter, and you already identify some of the furniture. And this is just a way that the agent can say, okay, go to this particular furniture at any point in the plan. We also have like what we call the long-term memory. So we have a time-wise aggregator. So every time we perform an action, we are going to condition on the previous action that we did and what we observed from those action. And we have a simple seek-to-seek transformer that was trained with in a seek-to-seek sequence, or yes, paradigm, and we used beam search as well to decode a couple of action candidates that we can do, and that helps us to have like a to do like a plan and try to, okay, if that plan doesn't work, we can just roll back a bit of the action and try a second plan. And the whole thing was trained with machine learning at the moment. So we had 2.5K games, about 100K episode. And that was trained in the text environment. So this is the text agent again. So there was no interaction with the simulator for this part. And then what we wanted to do, this is kind of the pre-training, and after that we are going to plug it inside the full bottler and then run the evaluation. So some video here during training. So on the actually after training the agent on some environment that we've seen during the training phase. I'm trying to get my mouse to, no, it doesn't work. Anyway, so what we see is like really short task that that the agent has to do. So put the cell phone in the safe. So you need to find the cell phone, open the safe, and then put it in. The other one was put a watch on the coffee table. There's also what we call in-distribution test. So we've seen the room before, but it's a new task. So requiring object that you didn't interact with during training time. So here it's put a watch. So you know what is a watch, you know what is a side table, but you never had to put the two together. And we have out of distribution. So you have an unknown room and an unseen task. So you might have seen the watch before, but maybe the safe wasn't there, or the object location were different, or the entire room layout or the texture were different as well. So that's for the generalization. And this is some of the result that we have after training the agent. So I guess I failed to mention, so what we've seen before, it's the oracle. It was not the agent, but this is the agent. So this is some success video. So right now what it was doing is the scanning that I was mentioning, just to get all the location. And then now it's trying to find where's the mug. So it's going to look at the cabinet because that's a reasonable place to do. And once it figure out it's not there, it look at the sink and finds it on the countertop. And then just remember where the microwave was, put it in it, close the door, and eat it. And then put it in the coffee machine. So it did the cup before and then put it in the coffee machine. That was like a non-task, but in an unseen room. And we have another one here. So play. Right. So put a watch in the safe that we saw before. So this is an unseen task in an unseen room. So it need to figure out where is the watch. So it's going to look at some places that I guess in the training set it was used to find a watch. Find it there. It's on the table, but it did open the drawer and realize it wasn't there, but then figure out, okay, it was in front of me. So it's not perfect. There's still some room for improvement. But yeah, it's all depend on what if it has experienced during the training and how we can adapt it. And then there's also some failure point. So this is like a fail example. So there's a task to put 2 soap bottles in the cabinet. That was a non-task in a scene room, but it still managed to fail it. And I think it's because the object was out of reach. Need to, yeah, takes a error too far away. So yeah, so it was trying to take the bottle that it sees in front of it, but it should have moved forward so that it can actually reach out. And because there's no, so we all our training was done in using imitation learning. So we don't have necessarily so the agent doesn't have the mechanism to realize that, oh, I made a mistake and I should actually correct for this plan. So what it experiences only like good trajectory from the expert to some extent. And this, yeah, so that's one of the type of failure that we observe. Yeah, so I put some graph here, but I think it's clear if you just look at the paper. What we wanted to show with this bar plot is just that there's like a wide variety of different tasks, and there's some easier tasks than others. So like the pick and place is way easier than if you have to pick 2 objects and place them, or you have to do some interaction like heating. So you need to heat and place something. You actually need to find the object and then find where to eat it, and then and this is for the zero-shot domain transfer. We did an ablation study. So what part of the module of the architecture, the bottle architecture, can we replace, and see what's the impact there. I don't want to talk too much about those, and I invite people that are interested in looking at the paper. Yeah, so that was a bit quicker than I expected, but so as future work, I did mention it a couple of times. So we want to do more like end-to-end training, or have like a more reinforcement learning approach, where we are going to be able to fine-tune maybe our agent. And the state estimator, instead of relying on some pre-trained mask RCNN, it would be nice to see if we can actually learn it on the fly while we have this text agent already providing some high-level sub-goals, and also the controller, which in this particular project we decided to not try to learn, because it's already like a problem in itself. But yeah, so any progress that it is made as vision or just controller could be integrated in this, I guess, framework for this agent, and hopefully will boost improvement or result on this environment or benchmark. And the other one that is something that is more like a dream project or ambitious project is to learn the text engine. So instead of relying on this having access to the PDDL description of the environment, and then having this text wall engine that can read those PDDL files, it would be nice if just by the interaction, what you see in the environment and the description of what happened in the environment given some action, can we learn this text wall engine? So this to learn this abstract planning. And there's recent work I should have put there about trying to do that, like learning grounding and with symbolic representation or symbolic reasoning, which is along those lines. So I guess that's it for the presentation. So if you have any question, either you can ask them here, or also available on the Slack channel for the IGLU contest. So you can reach me out there. So yeah, so we have a question. I guess there's a hand raised.
Thank you very much, Mark. Let me see who raised. Please unmute yourself if you have a question.
Yeah, can I go, or?
Yes.
Yeah, sure. Go ahead.
Sure. Yeah. Okay. Yeah. Thanks for your talk. It was very interesting to see. So maybe to dive right into it. So, did you observe any compositional behavior from the brain, as you call it, right? So, where you would be able to, for instance, chain kind of even the more abstract tasks, like picking up stuff and putting them down again, and would you be able to maybe sequence those one after the other, or what I'm asking is, are there like connectors like that embedded in the training data as well?
So just to make sure that I understood the question correctly. So are you talking about like multi-step planning? Like, can this text agent that we're training able to output like a sequence of action, or is something else?
Yeah, exactly. But then on the higher level, right? So not on the lower level.
Yeah, so on the higher level. Yeah. So in right, this particular text agent, like you saw the architecture, it was pretty simple. I doubt it can do that. So that's something we could actually monitor, but because it's conditioning on an observation of what happened, then it's difficult. So unless you have like some generative model that can actually produce either like in the latent space or a concretized observation, that would be difficult to do it in this particular environment. But I know that there's people working on that. Like either in this latent space, they are trying to do a state generation of what an action will do. And then if you have essentially it's RL world-based model-based RL, which has like this baked in their their architecture, they have some way of simulating what would be the result of an action, and that's definitely where my research is going on. Like, it's going in that particular direction. So I'm more and more interested in model-based RL and see if we can actually learn. And this is related to what I wanted to say by learning the text engine. So instead of relying on the text engine that tells you what is the outcome of your action, can you infer it and then just build on that and do multi-step reasoning? But that for sure would be like a mandatory thing to have if we want like good abstract planner. This is what humans do because we have some concept of what happened when we do certain action. But so
yeah, all right, thanks.
Yeah, long answer to say it doesn't right now, but that's definitely something that could be used.
Thanks. Is there any other questions?
I wanted to ask about the decoding. Like you mentioned that you use beam search. Like how hard, like how much did you have to play around with this decoding? Like, is it generating sequences that are not valid? Like how, like just tell us a bit more about your experiences on like what you have to look out for in this process.
Right. So I guess in this particular setup, it's a bit easier because those action, if you remember, those are high-level commands. So they usually like 4 words long. So those are not really long phrases, right? It's really short. And what I meant by the beam search is more, okay, it is in the decoding part of the agent, but it's more on, okay, let's try to have an action that says pick this object, and then another action that takes another object from the table and take or put down some objects. And so I have like a candidate list of action that could be used so we can either re-rank them before giving them to the controller. But in terms of playing with different, I guess, parameter or hyperparameter for the beam search, I don't think we played a lot with that. We just tried that and we saw that it actually improved because we can actually, if we try an action and we see that it is invalid, because that could be the case, then we can just fall on the second one. And then hopefully there's something that will produce interaction in the environment. I don't know if that answers your question or you have like a follow-up question.
No, that answered my question, thanks.
Thank you, Mark. Is there any other question from the audience?
Can I just ask a quick one?
Yes, please.
Yeah, sure.
Yep.
So there's like a mask RCNN, and then there's also like a transformer. Like there's a few pre-trained models, and then there's the dagger that you use, right? The imitation learning. So it seems like the butler itself, it's like a bunch of components put together. Did you try to like swap each of these like components with like something else that's maybe a bit, I don't know, cheaper or something easier to handle?
So with not for, yeah, so you're right about saying that it's like really like modular approach of building an agent, and that's what we aim right from the get-go, because in our head, if we want to solve this really challenging problem, let's try to reduce the complexity and fix some of the modules. So that's why in the especially in the controller, that we try to swap out different type of controllers. So more like on the Oracle side or some A-star planner that we don't have to learn and we can just exploit. And so this one, we did some ablation for the controller. For the vision, we did try a couple of them. I don't remember by heart, so I believe it's in the paper. But this one actually worked pretty decently. We did have an Oracle version of that, so you don't actually have to look at the image and decode it. So we just provide, there's an object there, and there, and there. And that obviously helped, because if your mask RCNN misses an object, that is important for the task, then no matter how good your plan is, it wasn't part of your observation, so you will fail. So that's, I think it's part of the result. And
that mask RCNN is pre-trained on like Coco or something.
No. Yeah, so that's maybe a caveat that we should mention. So it was trained on images from this environment. So we had so we started up an instance of an ALFWorld environment, and we moved the camera around. And because we have access to the simulator, we know where are the objects. So we have the ground truth annotation. So we did actually train this and end-to-end, like this mask RCNN, but it was tailored to our data.
End-to-end, like you train it separately. That's why you call it pre-train, and then you pick it up and use it in Butler.
Yes. But I meant like the mask RCNN was not using features from training on Cypher or something like that. Okay. That's what I meant by the end. Yeah, it's the pre-training that was done from scratch.
And the text agent is also pre-trained, yeah. In this case.
Yes. Yeah. It is pre-trained. Yeah, it's a pre-trained mask RCNN. Yes.
No, the text agent.
Yes.
Text, yeah. And that's pre-trained.
Yes.
From where?
It is pre-trained from. Let me go back here. Right. So here, because we have access to this TextWorld engine that is able to take an environment like one of the ALFWorld environment and convert it into a text-based game. So it's kind of this text agent was trained on text-based game. So the type of observation that we were getting from the TextWorld engine was super simple, and we see an example here. So on the dining table one, you see it label a laptop one, and a plate one, and a vase one, and so on. So this one, so why we went with the pre-training, because we could have done it during, I mean, there's no really other part for training, because the controller, we kept it fixed, and the state estimator was pre-trained. So there was no really a need for doing it end-to-end in this particular case. But running the 3D environment is like really slow, because you have to actually render the object, and then we have to run the mask RCNN and everything. Versus this is just text, it's super fast. So that's kind of another, I guess, point that we wanted to make, like advantage of this framework, is because when you can leverage a simpler environment, like an abstract environment, you can interact much faster, because you don't have to simulate physics, you don't have to simulate object detection, collision, and you can you can only use the abstraction that you need, so you don't necessarily need to go as deep as you want, and you're free to do so using language. So this pre-training was done. Essentially, we converted a bunch of ALFWorld environment into text-based game, and we run this text agent on those text-based game, and not just one at a time. It's like a collection of them. So because we wanted to improve generalization.
So I didn't follow this. So is this ground truth? So the text environment is that's not generated by a model?
That's it. That is correct. Yes. For the pre-training, yes. But at evaluation, so when we plug everything back into it, so if there's some text that is misgenerated because the mask RCNN failed to see some object, then that observation is provided to the text agent with missing information, and then the text agent has to figure out what to produce for the next action. But at that point, everything is kept fixed. So the evaluation is run like with the full pipeline.
Everything is kept fixed, like the embeddings are fixed.
Yeah, the embeddings are fixed, and we are not updating anything. We could, so we thought we could we would have time to actually do some fine tunings using RL. Because at this point, when you want to evaluate on a full environment, you get only a reward when you finish the task. So you're going to to be forced to use reinforcement learning here. We don't have imitation or expert trajectory. I mean, we could derive some, but
Cool.
I didn't fully get. So the state estimator, what's the formal description of a state? So what is it estimating?
so the state estimator is taking as input the image that the agent is seeing in the environment. So this is like a pixel image, and it has to convert it somehow into text because the text agent is expecting text representation. And the way we've done that is by running a mask RCNN to detect all the object in the image. And then this mask RCNN also produce a label for all the object that is detecting. So the label is the class of the object. So it's either a plate or a statue or something else. And we just use like an heuristic, like a really templated grammar way of generating the observation from what have been detected from the state estimator. I don't know if it's a bit clearer. So we have image,
Right.
detect objects. Yeah.
But you also have some other representation of the environment that is like representing the objects and their positions, or is that all in text?
It's all in text.
Okay.
What is provided to the text agent is text only. And we do this is actually an abstraction, so we don't have like particular special positioning that might not be relevant for this particular environment. So if you have two apples, if they are next to each other or really far, if they are on the same countertop, that is fine. That's enough information for the task at hand. So this like it shows how powerful language can be to do abstraction, because you don't necessarily care about the apple be touching or before. You only care that are they reachable because they are on the countertop and you are in front of the countertop or the dining table. Or
Okay, thanks.
so we are not claiming that we are doing like a end-to-end training process here. So I think we try to make sure that in the paper it was clear that this is an architecture that we propose for this particular environment that is modularized. So we have different modules that can be either taken independently or all together at the same time, depending on what you are interested in. So we are trying to reach out to people that are interested in vision and other people in robotic that are more interested in controller stuff.
And so maybe a follow-up is, did you also try to remove this O0? Because you mentioned that it was important for recognizing where the things were, right?
Yeah, we tried that. So this O0 is about describing what are the furniture. So you can see it as the object that cannot be moved. So that will be like the table, the fridge, the sink, that kind of stuff. And yeah, it was failing to go to other location because the way we were generating the command, there was nothing to condition on to know that, okay, yeah, you should go to the kitchen. I mean, in theory, because we have this recurrent layer in the that aggregate over time, it should be able to remember that, but just like making things harder. Yeah, but that's a fair point.
Okay. Is there any other questions or comments?
Yes, I have a question.
Please go ahead.
Yes.
Thank you, Marc, for your amazing lecture. So my question is, what is the the frames per second rate of your visual engine, which you were presenting today, and the speed of the textual environment?
I don't remember exactly the numbers on top of my head. I think we included a benchmark, a time benchmark comparison between the two in the paper. I want to say like it's maybe 20x or something. But the one of the major thing other than speed is how many instances you can run in parallel. Also, like if you want to do batch learning with Tor, if you have different environment that you have to load, that also takes a lot of RAM, GPU RAM, which what we want to do, what to use for the training. So versus in text, you can bunch like 1,000 of environment at the same time. That doesn't matter, and the speed has no impact. Like the bottleneck will be your agent taking a decision, like reading the sentence and so on. And
so
yeah.
So you mentioned the parallelization. So is there any batching available? I'm talking about the feature when you are able to like call the GPU rendering function, and it will return you like 2 or more instances of your observations rendered at the same time, of course.
You mean for the so we are using AI to Tor environment, or I guess Tor. So are you asking like, is it possible to run multiple environment at the same time and get all of those images at the same time?
Not quite. I'm talking about, so imagine in the first case, I can like run multiple processes of the environment, which, for example, can run synchronously. And in the other case, I can run one instance of the vectorized environment. And in this vectorized environment, I will send, for example, a tuples of actions, for example, 2 actions at the same time, and the environment would return me 2 observations at the same time. And these 2 observations would be rendered simultaneously.
Yes.
This implemented, for example, in such robotic environments as NVIDIA Isaac and Megaverse recently published.
So we are also doing that. I'm just saying that the amount of environment that you can run in parallel is limited. It depends on your amount of RAM that you have available for your GPU.
Mm-hmm. Okay.
And I don't remember how many, but it was way lower than 1,000 for text-based game. So, but we when we run the evaluation, we don't do it one at a time. So we run like multiple environment at the same time in parallel, like a vectorized environment.
Okay.
And so it also like demonstrated an approach, like I guess an opportunity or advantage of having this abstract that is less computationally expensive to run. You can do kind of mock-up planning, and then when you arrive at the actual embodied environment that maybe require more resource, or let's say in the real world, you don't want to spend a lot of time experimenting in the real world if you can do it in a I guess a wet lab or something else, like some abstract lab. I'm trying to look at the training, the speed. Yeah, I think so it was like 0.9 episode per second for the embodied world, and in the text world was 6.1 using an older version. So it is faster. It's not dramatically faster, but one of the other advantages, you can batch more of them, and you can spend a lot of time training.
Okay, thank you.
Thanks again, Mark. Is there any other questions from the audience?
Otherwise, for people that are watching it on YouTube, if you have access to the Slack channel, just ping me there.
Yes, indeed. You can always reach Mark and other mentors on the Slack channel. They agreed to help us. They volunteered basically. So please use this opportunity to ask your questions or ask for advice. So I think we are at the end of this invited lecture. Thank you very much again, Mark, for this very interesting lecture, and thanks everybody for attending and also for a very nice discussion afterwards. As Mark mentioned, you can find it on YouTube. We will immediately upload the video there, and you can follow up on Slack. Thanks everybody. Have a good day or night.
All right, thank you.
Thanks again. Bye-bye.
Goodbye.